June 15, 1944, Chengdu Airfield, Sichuan Province, China. Technical Sergeant Robert Morgan watched as maintenance crews loaded the final bombs into the bay of his B-29 Superfortress. The aircraft gleamed in the afternoon sun, its polished aluminum skin reflecting light across the tarmac like a mirror. At 99 feet in length with a wingspan stretching 141 feet, the bomber dwarfed every other aircraft on the field. But what would shock any observer who understood aviation engineering wasn't the size. It was what lay hidden inside that cylindrical fuselage. The crew compartments were sealed environments, maintaining 8,000 feet of pressure, even when the aircraft climbed to 30,000 feet. No heavy bomber in history had achieved this. American crews would fly to Japan in shirt sleeves, while enemy pilots struggled into bulky heated suits and oxygen masks just to reach half that altitude. The Japanese had nothing remotely comparable. This was the first combat mission against the Japanese home islands since the Doolittle Raid 26 months earlier. 75 B-29 seconds would strike the Imperial Iron and Steel Works at Yawata on Kyushu. The target lay 1,500 miles from Chengdu. No bomber except the Superfortress could reach it. The mission would introduce Japan to a technological revolution in aerial warfare that would ultimately destroy their ability to resist. But the journey to this moment had begun 4 years earlier, when American aeronautical engineers confronted a problem that seemed physically impossible to solve. How do you build a bomber that can fly higher, faster, and farther than anything in existence, while keeping the crew comfortable enough to function effectively for 16-hour missions? The answer would cost $3 billion, more than the entire Manhattan Project. It would require innovations in pressurization, fire control systems, and engine technology that pushed 1940s engineering to its absolute limits. And when Japanese forces finally captured intact examples and examined their construction, they would discover that American industry had achieved capabilities Japanese engineers considered beyond the current state of the art. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The specifications that led to the B-29's creation arrived at Boeing's Seattle offices in January 1940. The United States Army Air Corps issued requirements that seemed designed to be impossible: maximum speed of 400 miles per hour, service ceiling of 35,000 feet, range exceeding 5,000 miles, bomb load of 2,000 pounds at maximum range or 20,000 pounds for shorter missions, and one additional requirement that would define every design decision that followed: pressurized crew compartments. No production bomber had ever achieved this. The technology existed in experimental form. Boeing had developed pressurization for their Model 307 Stratoliner commercial airliner in 1938, but applying it to a combat aircraft presented challenges that multiplied exponentially. A bomber needed multiple crew positions. It needed gun turrets. It needed bomb bays that had to open at altitude. Every one of these requirements conflicted fundamentally with maintaining cabin pressure. The engineering team at Boeing understood immediately that conventional solutions wouldn't work. Chief Engineer Edward Wells assembled a design team that included George Scherer for aerodynamics and Wellwood Beale for overall project management. They began with first principles, questioning every assumption about bomber construction. The fuselage had to be circular in cross-section throughout its entire length. This was non-negotiable. Pressurization required a perfect cylinder to distribute stress evenly across the structure. Any flat surfaces or irregular shapes would create stress concentration points that would fail catastrophically under repeated pressurization cycles. The circular fuselage meant they couldn't use traditional flat-sided construction. Every structural member had to curve to match the fuselage contour. The aluminum skin had to be substantially thicker than conventional aircraft. Where typical bombers used skin measuring 0.04 inches thick, the B-29 would require 0.1875 inches throughout most of the fuselage and inner wing sections. This massive increase in skin thickness added thousands of pounds to the empty weight, but it was absolutely necessary. The pressurization system would maintain an 8,000-foot cabin altitude, while the aircraft flew at 30,000 feet. This meant a pressure differential of 8 pounds per square inch, pushing outward on every square inch of fuselage surface. Without thick skin and robust internal framing, the fuselage would rupture like an overinflated balloon. The gun turret problem seemed insurmountable at first examination. Conventional bombers positioned gunners directly at their weapons, sitting in open or lightly enclosed positions exposed to the slipstream. This was impossible with pressurization. Opening gun positions to the external atmosphere would instantly decompress the cabin, incapacitating or killing the crew within minutes at high altitude. General Electric received the contract to solve this problem in 1941. Their engineers developed the Central Fire Control System, the most sophisticated analog computing device ever installed in an aircraft. 5 separate computing units, each weighing 200 pounds and containing thousands of mechanical and electrical components, would calculate firing solutions automatically. The system measured airspeed from pitot tubes, altitude from barometric sensors, outside air temperature from thermocouples, and target range from optical sights. It compensated for gravity drop, wind drift, temperature effects on air density, and the ballistic characteristics of 50 caliber ammunition. 4 remote turrets, each containing 2 Browning M2 machine guns, could be controlled by any of 5 gunner stations through an elaborate system of Celsyn's electrical motors that transmitted control movements instantaneously. The gunner aimed through a computing gun sight. The Central Fire Control System automatically adjusted the gun's pointing angle to account for all ballistic factors. The effective range increased to 900 yards, 50% greater than manually aimed guns, and more than twice the effective range of most Japanese fighter armament. But this sophistication came at a brutal cost in complexity and weight. The complete system weighed over 2,000 pounds. Early production aircraft suffered constant failures. Electrical connections corroded, mechanical linkages jammed, computing units overheated. Factory workers building the first B-29 seconds had never seen technology this advanced. Many were women with no previous manufacturing experience, recruited to replace men sent to combat. They struggled to assemble systems requiring precision far beyond conventional aircraft construction. The engine selection created the most dangerous problem the B-29 would face. Wright Aeronautical's R3350 duplex Cyclone produced 2,200 horsepower, making it the most powerful piston engine in production anywhere in the world. But it was also the most temperamental and fire-prone engine ever installed in quantity production aircraft. The 18-cylinder radial had been rushed into service without adequate testing. The crankcase used magnesium alloy to save weight. Under high power settings, especially during takeoff and climb, the cylinders overheated, exhaust valves stuck, pistons seized, and when failures occurred, magnesium burned with a brilliant white flame that could melt through wing spars in under a minute. The wing spars were particularly vulnerable. These massive aluminum beams, with flanges weighing 255 pounds each, provided the structural strength to support the aircraft's loaded weight of 140,000 pounds, but they passed directly behind the engine nacelles. An engine fire could breach the spar, causing catastrophic structural failure and wing separation. More B-29 crews would die from engine fires than from Japanese fighters during the first year of operations. The fuel system required revolutionary design to accommodate both pressurization and the enormous range requirements. The B-29 carried 9,400 gallons of aviation fuel in 14 separate tanks distributed throughout the wings and forward fuselage. At £7 per gallon, this represented 65,800 pounds of highly flammable liquid. Unlike Japanese bombers with their unprotected tanks, every B-29 fuel cell featured self-sealing technology. Multiple layers of rubber compound lined each tank. When punctured by bullets or shell fragments, the rubber swelled on contact with fuel, sealing holes automatically and preventing both fuel loss and fire. This protection added 1,800 pounds to the aircraft's empty weight. But combat experience over Europe had proven the technology essential. B-17 and B-24 bombers with self-sealing tanks showed survival rates 3 to 4 times higher than earlier aircraft with unprotected fuel systems. American doctrine considered crew protection non-negotiable, regardless of weight penalties. The 3 pressurized compartments represented the most ambitious pressurization system ever attempted in a production aircraft. The forward compartment housed the pilot, co-pilot, flight engineer, navigator, bombardier, and radio operator. A long tunnel, 34 inches in diameter, ran over the bomb bays, connecting forward and aft compartments. The aft compartment held 3 gunners and the radar operator. The tail gunner occupied a separate pressurized position isolated at the aircraft's rear. WWII research designed the pressurization system with multiple redundancies. Engine-driven superchargers compressed outside air. Heat exchangers cooled it to 70 degrees Fahrenheit. Pressure regulators maintained 8,000-foot cabin altitude automatically up to 30,000 feet. Sound-dampening fiberglass blankets lined the compartments, reducing engine noise that would otherwise be deafening. The system worked flawlessly in testing, but under combat conditions with battle damage, pressurization failures would become routine. Small-caliber bullets punched holes that could be plugged with rags or jackets. Larger damage required emergency depressurization and donning oxygen masks while descending to breathable altitudes. The bomb bays posed a seemingly insoluble contradiction. They had to remain unpressurized because opening pressurized bomb bay doors would cause explosive decompression. But the pressurized crew compartments needed to remain sealed. The solution was simple but absolute. The tunnel connecting forward and aft compartments ran through the unpressurized bomb bay section. Crew members could crawl through the tunnel only while pressurized. The tail gunner could enter or exit his position only when the aircraft was depressurized below 10,000 feet. Once pressurized for high-altitude flight, the tail gunner was isolated for the entire mission, unable to leave his station for any reason. The first B-29 prototype lifted off from Boeing Field in Seattle on September 21, 1942. Test pilot Edmund Allen commanded the flight. Everything functioned perfectly for 30 minutes. Then an engine fire erupted in the No. 1 nacelle. Allen attempted to return to Boeing Field, but the fire spread too rapidly. Flames melted through the wing spar. The wing failed. The prototype crashed into a meat-packing plant, killing Allen, his crew, and 19 workers on the ground. Investigation revealed that the R-3,350 engines needed extensive redesign. But production orders had already been placed for over 1,600 aircraft. General Henry Arnold, commanding the Army Air Forces, refused to delay deployment. The B-29 would go to war with inadequately developed engines because the strategic situation demanded it. Japan controlled the Western Pacific. No existing American bomber could reach Japanese industry from available bases. The B-29 was the only weapon that could strike at Japan's war-making capacity. Political pressure from President Roosevelt intensified the urgency. The 1944 election approached. Roosevelt needed visible progress against Japan to counter Republican criticism of his conduct of the Pacific War. Manufacturing the B-29 became the largest aircraft production effort in history. 4 main assembly plants operated simultaneously. Boeing built aircraft at Renton, Washington, and Wichita, Kansas. Bell Aircraft operated a plant at Marietta, Georgia. Martin built B-29 seconds at Omaha, Nebraska. Thousands of subcontractors supplied components. The complexity overwhelmed the manufacturing system initially. By January 1944, only 16 of 97 completed aircraft were flyable. Parts shortages created a logistics nightmare. Modifications required at the factory weren't completed, forcing aircraft to sit at modification centers waiting for rework. General Arnold visited the Wichita plant on January 1, 1944. He demanded 175 combat-ready aircraft by March 1. 8 weeks later, the situation had barely improved. Arnold assigned Brigadier General Kenneth Wolfe to command the XX Bomber Command, the first B-29 combat organization. Then he sent Brigadier General Bennett Myers to Kansas with unlimited authority to break the production bottleneck. The Battle of Kansas began. Specialists flew in from every corner of the country. Assembly line workers were reassigned to modification duties. Subcontractors received orders to prioritize B-29 components above all other contracts. Supplies arrived by aircraft, train, and truck 24 hours daily. Every aircraft required extensive modifications after leaving the assembly line. Wing structures needed reinforcement. Pressurization panels in the nose had to be replaced. The panels initially installed were optically distorted, making landing distance judgment nearly impossible. Each replacement panel required pressure testing individually. Electrical systems needed rewiring. Gun turrets required adjustment and calibration. The work proceeded around the clock. By late March, combat-ready aircraft began reaching operational units. The XX Bomber Command deployed to India between February and May 1944. Airfields around Calcutta were expanded to handle B-29's weight and size requirements. Runways had to be longer and stronger than conventional bomber fields. A fuel pipeline was constructed from Calcutta harbour to the airfields because rail transportation couldn't handle the volume. Chinese labourers, numbering in the tens of thousands, built these bases using hand tools. Each airfield required a runway 8,500 feet long and capable of supporting aircraft weighing 140,000 pounds at takeoff. The logistics were staggering. Each B-29 combat mission from China required flying supplies over the Himalayas from India. The supply flights, nicknamed Flying the Hump, consumed enormous resources. 7 B-29 supply missions were required to support one combat mission. The aircraft carried their own fuel and bombs from India to China, then refueled in China for missions against Japan. The inefficiency was recognized immediately, but alternatives didn't exist. The Mariana Islands wouldn't be captured until later in 1944. China offered the only bases within B-29 range of Japan. The first combat mission launched on June 5, 1944. 98 B-29 seconds departed Indian bases to attack rail facilities at Bangkok, Thailand. This was a training mission, deliberately chosen to be less challenging than missions against Japan. 10 aircraft were dispatched, but 98 actually launched. Mechanical problems had already reduced numbers. The formation encountered monsoon weather. 14 aircraft aborted due to mechanical failures. 5 were lost to accidents. The surviving aircraft attacked Bangkok with minimal opposition. The mission achieved its training objectives, providing crews with combat experience and revealing operational problems that needed correction. 10 days later came the main event, the first B-29 strike against the Japanese home islands since the Doolittle Raid. 75 aircraft departed Chengdu loaded with 500-pound bombs. The target was the Imperial Iron and Steel Works at Yawata on Kyushu. Weather was perfect. Japanese radio broadcasts had announced B-29 deployments to China, eliminating any element of surprise. But Japanese defenses proved inadequate. Few fighters could reach the B-29's bombing altitude. Anti-aircraft fire was inaccurate. Only 47 aircraft actually bombed near the primary target. Navigation challenges, mechanical problems, and fuel concerns scattered the formation. 1 B-29 was lost to fighters. 4 crashed due to mechanical failures. The damage to Yawata was negligible. Post-mission analysis revealed that bombing from extreme altitude produced terrible accuracy, but the psychological impact was profound. Japanese civilians saw American bombers over the home islands for the first time since 1942. The myth of Japanese invulnerability shattered. American media celebrated the mission as a great success, providing exactly the positive narrative President Roosevelt needed for the election campaign. But for B-29 crews, the mission revealed the aircraft's immature state. Engine fires remained endemic. Electrical systems failed regularly. The central fire control system malfunctioned frequently. Pressurization leaks were common. The aircraft demanded constant maintenance far beyond any previous bomber. Ground crews worked 20-hour days, keeping aircraft flyable. Parts shortages meant cannibalizing one aircraft to keep others operational. The missions from China continued through the summer and fall of 1944. Targets included steel plants, aircraft factories, and shipping facilities across Japan, Manchuria, and Southeast Asia. Loss rates from mechanical failures exceeded combat losses. The joke among crews was that Wright Aeronautical and Curtiss Wright, makers of the R-3350 engines, were killing more Americans than the Japanese. The jest had bitter truth. Engine fires during takeoff killed entire crews when aircraft couldn't gain sufficient altitude for bailout. Engines failing mid-mission forced aircraft to ditch in the ocean or attempt landings at emergency fields throughout China. Japanese fighter pilots quickly learned that attacking B-29 seconds required tactics far different from opposing earlier American bombers. The Superfortress flew too high and too fast for conventional interception. Pilots needed to gain altitude ahead of the formation, then dive through at maximum speed. The brief firing pass had to achieve kills immediately because the B-29's speed prevented prolonged engagements. The central fire control system, when functioning properly, made massed fighter attacks suicidal. Gunners could concentrate multiple turrets on single targets. The 900-yard effective range meant B-29 gunners could fire accurately before Japanese fighters entered their own effective range. But Japanese forces also learned the B-29's vulnerabilities. The pressurization system created fatal weaknesses. 20mm cannon shells that penetrated pressurized compartments caused violent decompression. Crews scrambling for oxygen masks lost precious seconds. Wounded crew members in depressurized aircraft died from oxygen deprivation before receiving medical attention. The thick aluminum skin that enabled pressurization also made the aircraft heavier and less maneuverable than earlier bombers. Damaged B-29 seconds couldn't take evasive action. They either maintained formation or fell behind where fighters concentrated attacks. Japanese technical intelligence officers examined every crashed B-29 they could reach. Wreckage scattered across Kyushu from the June 15th mission provided the first detailed look at American Superfortress construction. What they found revealed a level of technological sophistication that exceeded anything in Japanese production or even advanced development. The pressurization system's complexity shocked examining engineers. The ducting ran throughout the fuselage, connecting superchargers to crew compartments through regulators, valves, and heat exchangers. Japanese engineers had theoretical knowledge of cabin pressurization. Several experimental aircraft programs had explored the concept, but translating theory into operational hardware at production line scale was entirely different. The B-29 system worked reliably enough for combat operations despite its complexity. Japanese industry couldn't duplicate this achievement with available resources and manufacturing capability. The central fire control system's sophistication was even more alarming. Examining engineers carefully dismantled computing units recovered from crash sites. The mechanical precision astounded them. Gear trains calculated ballistic trajectories using cams, linkages, and differential mechanisms machined to tolerances, measuring thousandths of an inch. The analog computers incorporated dozens of vacuum tubes and thousands of passive components. The Celsin motors that transmitted control movements required precise electrical characteristics to maintain synchronization. Japanese industry could build individual components given sufficient time and resources, but producing thousands of complete systems for installation in production aircraft was beyond current manufacturing capacity. The engine nacelles revealed another troubling disparity. The R-3350 engines, despite their fire-prone characteristics, generated 2,200 horsepower each. The B-29's 4 engines combined produced 8,800 horsepower total. Japan's most powerful production engine, the Mitsubishi Ha-42, produced barely 2,200 horsepower and existed only in prototype form. The best engines in production service generated approximately 2,000 horsepower. The four-engine G-8N Renzan bomber, Japan's attempt to match B-29 capability, used engines producing 1,800 horsepower each for 7,200 horsepower total. This 22% power deficit translated directly to inferior speed, sealing, and payload performance. The self-sealing fuel tanks demonstrated another fundamental difference in design philosophy. Japanese engineers examining B-29 wreckage found fuel cells with multiple rubber layers totaling nearly 1 inch in thickness. When punctured, the rubber compound swelled on contact with fuel, automatically sealing holes and preventing catastrophic fuel loss or fire. The weight penalty was substantial, approximately 1,800 pounds per aircraft, but the survival advantage was equally calculable. American combat data from Europe showed that bombers with self-sealing tanks survived battle damage at rates 3 to 4 times higher than unprotected aircraft. Japanese engineers understood the technology. They had examined self-sealing systems in captured American fighters as early as 1942. But implementing the technology across bomber production required rubber compounds, manufacturing processes, and quality control that Japanese industry struggled to achieve. The few Japanese aircraft that received any fuel tank protection used thin rubber sheets that provided minimal benefit compared to American standards. The fundamental calculation differed between nations. American doctrine valued crew survival and aircraft recovery above maximum performance. Japanese doctrine accepted catastrophic vulnerability in exchange for range and speed advantages. The structural reinforcement throughout the B-29 revealed American engineering conservatism. Longerons spaced every 8 inches provided redundant load paths. Thick aluminum skin distributed stresses broadly. The wing spars, with their 255-pound flanges, were massively overbuilt by Japanese standards. This structural redundancy meant the B-29 could absorb battle damage that would destroy lighter aircraft, crews reported. Returning from missions with holes measuring several feet in diameter punched through wings or fuselage. The redundant structure kept the aircraft flyable despite damage that appeared catastrophic. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By November 1944, the strategic situation had shifted dramatically. American forces captured Saipan, Tinian, and Guam in the Mariana Islands during summer fighting that cost over 3,000 American dead and 13,000 Japanese defenders killed. The Marianas lay only 1,500 miles from Tokyo. More importantly, they offered flat terrain suitable for massive airfield construction, deep water harbors for supply ships, and security from Japanese ground attack. The decision was made to shift B-29 operations from China to the Marianas. 5 major airfields were constructed across the 3 islands, 2 on Flat, Tinian, 1 on Saipan, and 2 on Guam. Navy construction battalions began work even before ground fighting ended. The scale dwarfed anything attempted previously in the Pacific. Each field required runways 8,500 feet long, parking areas for over 100 aircraft, fuel storage for millions of gallons, bomb storage for thousands of tons, and support facilities for thousands of personnel. The work proceeded 24 hours daily. By October, the first B-29 seconds arrived. The XXI Bomber Command, commanded by Brigadier General Haywood Hansell, began operations from the Marianas on November 24, 1944. 111 B-29 seconds departed Saipan, targeting the Nakajima aircraft factory at Musashino near Tokyo. Weather was terrible. Heavy clouds obscured the target. Only 24 aircraft bombed the primary target. The others scattered bombs across Tokyo or aborted entirely. 1 B-29 was lost. The mission demonstrated that high-altitude precision bombing faced severe challenges over Japan. Weather patterns, especially the jet stream at high altitude, created wind speeds exceeding 200 miles per hour. Bombardiers couldn't compensate for such powerful winds. Bombs scattered wildly despite the sophisticated northern bombsight technology. Japanese air defenses improved rapidly once B-29 seconds began operating regularly from the Marianas. Fighter units equipped with improved aircraft concentrated at airfields around Tokyo and other industrial centers. The Kawanishi N-1K Shiden, Kawasaki Ki-100, and Mitsubishi J-2M Raiden featured better high-altitude performance than earlier fighters. Pilots developed ramming tactics called Tayatari, deliberately flying into B-29 seconds when ammunition was exhausted. This desperation tactic revealed Japan's deteriorating military situation, but also demonstrated the determination of fighter pilots to stop the bombers regardless of personal cost. Anti-aircraft defenses concentrated around vital targets. Japanese industry manufactured tens of thousands of anti-aircraft guns, ranging from small-caliber machine guns to 88mm and 100mm heavy weapons. Barrage fire at high altitude created defensive boxes that B-29 formations had to penetrate. While individual accuracy was poor, massed fire achieved results through sheer volume. Damaged B-29 seconds falling behind formations became targets for concentrated fighter attacks. The first months of Marianas operations produced disappointing results despite enormous effort and expenditure. High-altitude precision bombing simply didn't work under Japanese weather conditions. Targets were rarely visible through clouds. The jet stream scattered bombs unpredictably. Even when bombs hit target areas, damage to dispersed Japanese industry was minimal. Japanese factories operated in small workshops throughout urban areas, rather than concentrated in large plants. Destroying a few buildings had negligible impact on production. In January 1945, Major General Curtis LeMay arrived to command XXI Bomber Command, replacing Hansel. LeMay had commanded B-17 operations over Europe, and understood that doctrine must adapt to circumstances. He studied the problem methodically. High-altitude bombing wasn't working. Japanese defenses at high altitude were strengthening. Something had to change drastically, or the entire B-29 program would fail to achieve strategic objectives. LeMay made a decision that shocked his subordinates. B-29 seconds would attack at night from low altitude, using incendiary bombs against urban industrial areas. The change was revolutionary and terrifying. Low altitude meant flying at 5,000 feet, well within range of light anti-aircraft guns and searchlights. Night attacks prevented fighters from intercepting effectively, but also made formation flying nearly impossible. Each bomber would attack individually. Incendiary bombs would create firestorms in cities constructed primarily of wood and paper. The civilian casualties would be massive. The tactical justification was coldly logical. Japanese industry operated in small workshops integrated into residential neighborhoods. Workers lived adjacent to production facilities. Destroying the workshops also destroyed the workers' homes and killed the workers themselves. This wasn't precision attack on military targets. This was area bombing designed to destroy Japan's ability to produce war materials by destroying the infrastructure and workforce simultaneously. The first low-altitude incendiary mission launched on March 9, 1945. Over 300 B-29 seconds struck Tokyo carrying M69 incendiary clusters. Each aircraft carried 7 tons of incendiaries. The bombs scattered submunitions that ignited on impact, spreading napalm fires that couldn't be extinguished with water. The attack concentrated on a 3-by-4-mile area of eastern Tokyo, where small factories and dense residential neighborhoods intermingled. The results exceeded every projection. Firestorms developed as thousands of individual fires merged into conflagrations that created their own weather. Superheated air rose violently, creating ground-level winds exceeding 60 miles per hour that fed oxygen to the flames. Temperatures reached 1,800 degrees Fahrenheit. People caught in the open died from heat exposure before flames reached them. Canals and rivers filled with bodies of people who jumped in seeking relief from heat and smoke but drowned or died from steam burns. 16 square miles of Tokyo were destroyed completely. Conservative estimates placed deaths at 80,000. The number may have exceeded 100,000. Over 1 million people were rendered homeless. The single night's destruction exceeded the damage from any previous bombing raid in history, surpassing even the Hamburg firestorm of July 1943 or the Dresden raids of February 1945. For B-29 crews, the mission was traumatic. Flying at 5,000 feet, they could see people running in the streets below. The smell of burning flesh penetrated aircraft despite closed windows. Turbulence from rising heat threw aircraft around violently. Some crews vomited from the smell, others refused to look down. But the tactical results vindicated LeMay's gamble. 14 B-29 seconds were lost, barely 4% of the attacking force. Japanese fighters, expecting high-altitude attacks, were caught completely unprepared. Anti-aircraft gunners couldn't depress their weapons sufficiently to engage low-flying bombers. The campaign intensified. Nagoya was struck on March 11th, Osaka on March 13th, Kobe on March 16th. By mid-March, every major Japanese city except Kyoto had been attacked at least once. Japanese firefighting capabilities collapsed under the sustained assault. Equipment was inadequate. Training was insufficient. Water pressure was too low. Civil defense. Volunteers died by thousands attempting to fight fires that defied all control measures. Japanese civilians' morale plummeted. Surveys conducted after the war revealed that by March 1945, over 60% of urban residents believed Japan would lose the war. The visible destruction of cities demonstrated that American air power could strike anywhere at will. No defense could stop the B-29 seconds. The imperial government's promises of victory rang hollow when entire neighborhoods burned nightly. Japanese fighter pilots fought with desperate courage, but insufficient numbers and inadequate aircraft. The best pilots had died in earlier campaigns across the Pacific. Replacement pilots had minimal training and limited flying hours. Fuel shortages restricted training further. Many pilots had under 100 hours total flight time when assigned to combat units. American B-29 gunners reported fighter attacks that showed more determination than skill. Pilots flew directly at bombers firing continuously, often ramming when ammunition exhausted. These suicide tactics occasionally destroyed B-29 seconds, but couldn't stop the formations or even slow the campaign significantly. The capture of Iwo Jima in February and March 1945 provided emergency landing fields for damaged B-29 seconds returning from Japan. The island lay directly on the flight path between the Marianas and Tokyo. B-29 seconds could reach Iwo Jima with battle damage or mechanical failures that would have forced ditching in the ocean otherwise. By war's end, over 2,400 B-29 emergency landings occurred at Iwo Jima's airfields. Crew members saved numbered in the thousands. The island's capture, which cost nearly 7,000 American dead and 19,000 wounded, was justified by many historians solely based on its value as an emergency field for B-29 operations. Japanese technical intelligence efforts to understand B-29 technology continued throughout 1945. Every crashed bomber was examined thoroughly. Components were recovered for detailed analysis. Captured crew members were interrogated about aircraft systems and performance. The information gathered revealed the enormous technological gap that had developed between Japanese and American aviation. The Kawasaki Ki-91 program represented Japan's most ambitious attempt to match B-29 capabilities. Design work began in May 1943, responding to the Army's requirement for a long-range heavy bomber capable of striking American bases. The specifications called for a 4-engine aircraft with pressurized cabin, heavy defensive armament, and range exceeding 6,000 miles. The design incorporated knowledge gained from examining captured B-29 components. The planned power plant was 4 Mitsubishi Ha-214 engines, each generating 2,500 horsepower. The armament would include 12 20mm cannons in remotely controlled turrets, but the Ki-91 never flew. By April 1944, a wooden mock-up was complete and prototype construction had begun. Then B-29 raids commenced against Japan. In February 1945, a B-29 raid destroyed the Gifu prefecture facility, where the 60% complete prototype was being built. The program was suspended. Even if the prototype had flown successfully, Japanese industry lacked the capacity to produce Ki-91 seconds in meaningful numbers. The technological sophistication required exceeded available manufacturing capability. The pressurization system particularly challenged Japanese engineers. Examining crashed B-29 seconds revealed system complexity that required manufacturing precision Japanese industry struggled to achieve. The ducting, valves, regulators, and heat exchangers demanded tight tolerances and leak-free construction. The control systems needed reliable operation through thousands of pressurization cycles. Japanese experimental aircraft with pressurization suffered chronic reliability problems. The systems worked briefly under test conditions but failed in operational service. American engineers had solved these problems through years of development and extensive testing. Japanese engineers lacked the time and resources to match this achievement. The analog computing fire control systems similarly exceeded Japanese manufacturing capabilities. Disassembling captured computing units revealed mechanisms of extraordinary precision. The gear trains used hardened steel components machined to tolerances measuring thousandths of an inch. The cams that calculated ballistic corrections had complex three-dimensional profiles, requiring specialized equipment to manufacture. The vacuum tubes needed consistent electrical characteristics to function reliably in computing circuits. Individual Japanese companies could produce such components given sufficient time. But manufacturing thousands of complete systems for installation in production aircraft was impossible with wartime resource, constraints, and competing priorities. By summer 1945, the B-29 campaign had effectively destroyed Japan's ability to wage war. Industrial production collapsed. Over 60 cities had been burned extensively or completely destroyed. Transportation networks were disrupted by mining operations that closed major ports. Oil refineries were destroyed. Coal supplies couldn't reach factories. Workers couldn't reach surviving production facilities. Food supplies dwindled as agricultural distribution systems broke down. Military forces throughout the empire couldn't be supplied or reinforced. American B-29 strength in the Marianas reached 1,000 aircraft by July. Command personnel numbered over 75,000 across Guam, Tinian, Saipan, and Iwo Jima. Monthly bomb tonnage exceeded 40,000 tons. Missions involving 500 or more bombers became routine. Japanese air defenses had been reduced to negligible effectiveness. Fighters rarely appeared. Anti-aircraft fire decreased as ammunition stocks were exhausted. B-29 seconds began flying unopposed daylight missions, demonstrating complete American air superiority. On August 6, 1945, the B-29 Enola Gay, commanded by Colonel Paul Tibbets, departed Tinian carrying a single atomic bomb. The aircraft was a silverplate variant specially modified for nuclear weapons delivery. Defensive armament was removed to save weight. Special bomb bay modifications accommodated the 10,000-pound weapon. The target was Hiroshima, a city of 350,000 deliberately spared from earlier incendiary raids to provide a clear demonstration of atomic destructive power. At 08:15 local time, Bombardier Major Thomas Ferriby released the weapon from 31,000 feet. The Enola Gay executed a violent 155-degree diving turn to escape the blast radius. 43 seconds later, at 1,900 feet altitude, the weapon detonated. The explosion equaled 16 kilotons of TNT. The fireball temperature exceeded 1 million degrees. Everything within 1 mile of ground zero was vaporized or incinerated instantly. Blast waves destroyed buildings throughout a 2-mile radius. Over 70,000 people died immediately. Total deaths eventually exceeded 140,000, including radiation effects. 3 days later, on August 9th, the B-29 Boxcar, commanded by Major Charles Sweeney, struck Nagasaki with a second atomic bomb. The primary target was Kokura, but weather prevented visual bombing. Boxcar diverted to the secondary target. At 11:02 local time, the weapon detonated over Nagasaki with a yield of 21 kilotons. Over 40,000 people died immediately. Total deaths reached approximately 70,000. Emperor Hirohito announced Japan's surrender on August 15, 1945. The formal surrender ceremony occurred aboard USS Missouri in Tokyo Bay on September 2nd. As Japanese representatives signed the surrender documents, over 400 B-29 seconds flew in formation over the bay. The sight symbolized the technological and industrial superiority that had decided the Pacific War. Japan's military forces remained substantial, with over 2 million troops and thousands of aircraft prepared for homeland defense. But the combination of atomic weapons, continuing conventional bombing, and complete blockade made further resistance meaningless. The B-29's technological advantages had proven decisive. Pressurized cabins allowed crews to fly in comfort at altitudes Japanese fighters struggled to reach. The massive four-engine power enabled payload and range that no Japanese bomber could match. Self-sealing fuel tanks and structural redundancy provided survival capabilities that Japanese aircraft lacked. The central fire control system created defensive firepower that made massed fighter attacks prohibitively costly. Most importantly, American industrial capacity produced over 3,900 B-29 seconds, while Japanese industry managed fewer than 100 of their most advanced bombers. Japanese engineers who examined B-29 wreckage throughout the war understood that American technological sophistication exceeded their own capabilities by years of development. The pressurization systems, analog computers, powerful engines, and robust construction demonstrated engineering maturity that Japanese industry couldn't replicate with available resources and time. Individual components could be copied, but the integration of multiple advanced systems into a reliable production aircraft required manufacturing infrastructure and engineering experience that took years to develop. The Soviet Union demonstrated this challenge when they reverse-engineered captured B-29 seconds into the Tupolev Tu-4. 4 B-29 seconds made emergency landings in Soviet territory during 1944 and 45. Stalin ordered them copied exactly. The project required over 900 Soviet enterprises, working for 2 years. The first Tu-4 flew in May 1947, 2 years after the war ended. Even Soviet industry, with its substantial resources and captured complete aircraft, needed that long to duplicate B-29 technology. For Japan, fighting a desperate defensive war with collapsing industry and dwindling resources, matching B-29 capabilities was impossible. The technological gap between Japanese and American aviation had widened steadily throughout the war. By 1945, that gap had become unbridgeable. Japanese fighters from 1941 dominated early war engagements through superior maneuverability. But by 1945, American aircraft exceeded Japanese performance in speed, altitude, firepower, and survivability. The B-29 epitomized this transformation. The pressurization technology that seemed so revolutionary in 1944 became standard in post-war aviation. Boeing's experience with B-29 pressurization led directly to commercial airliners like the Stratocruiser. The principles developed for military bombers enabled comfortable long-distance passenger flight at high altitude. Modern jet airliners all use pressurization systems descended directly from B-29 technology. The analog computing fire control systems evolved into early digital computers. The precision manufacturing required for B-29 production advanced American aerospace industry capabilities that dominated post-war aviation development. The aircraft that Japanese engineers examined in crashed examples across their homeland represented more than advanced technology. It represented an entire industrial system capable of designing, producing, and deploying revolutionary weapons in massive quantities, while simultaneously fighting wars across the Pacific and supplying allies fighting in Europe. The B-29's $3 billion development cost exceeded Japan's entire annual military budget. American industry produced over 3,900 B-29 seconds, while maintaining production of tens of thousands of fighters, medium bombers, transport aircraft, and naval vessels. This industrial capacity, more than any individual technological advantage, determined the Pacific War's outcome. Japanese military doctrine in 1941 assumed that initial victories would create a defensive perimeter that American forces couldn't penetrate. The assumption proved catastrophically wrong. American industrial capacity, technological innovation, and strategic bombing capability combined to overwhelm Japanese defenses despite determined resistance. The B-29, with its pressurized cabin that allowed comfortable high-altitude flight, symbolized the technological revolution that made Japanese defeat inevitable. When Japanese engineers climbed through wreckage of crashed B-29 seconds, examining the pressurization ducting, the thick aluminum skin, the sophisticated fire control computers, and the powerful engines, they understood they were witnessing capabilities their nation couldn't match. The realization came too late to affect the war's outcome. By the time B-29 seconds appeared over Japan, the industrial and technological advantages they represented had already decided the conflict. The Japanese could study the technology, understand the principles, and admire the engineering achievement. But they couldn't duplicate it, and they couldn't defend against it. The last B-29 combat mission flew on August 14, 1945, hours before surrender was announced. Over 800 superfortresses struck targets across Japan in the final demonstration of American air power. Japanese fighters made no serious attempts at interception. Anti-aircraft fire was sporadic and ineffective. The mission was a victory lap, showing complete American dominance of Japanese airspace. When the war ended, B-29 seconds began supply drops to prisoner-of-war camps throughout Japan and occupied territories, delivering food and medicine to thousands of Allied prisoners. The bombers that had burned Japanese cities now sustained lives, demonstrating their versatility. The B-29's legacy extended far beyond World War II. The aircraft flew combat missions throughout the Korean War from 1950 to 53. Modified versions served as tankers, reconnaissance platforms, and rescue aircraft through the 1960s. The Soviet Tu-4 reverse-engineered copy introduced Russian aviation to modern strategic bombing capabilities that shaped Cold War nuclear strategy. Commercial derivatives like the Boeing 377 Stratocruiser carried passengers across oceans in pressurized comfort, revolutionizing air travel. But the most profound legacy was technological. The B-29 demonstrated that advanced features previously considered experimental could be integrated into production aircraft and deployed operationally at scale. Pressurization, remote-controlled weapons, analog computing fire, control, powerful turbocharged engines, and sophisticated systems integration all became standard features in subsequent military and commercial aircraft. The engineering challenges overcome in B-29 development established capabilities and manufacturing processes that dominated aerospace industry for decades. For Japanese engineers examining crashed B-29 seconds in the ruins of their burned cities, the aircraft represented both technological marvel and instrument of defeat. They could appreciate the engineering sophistication while confronting the reality that their nation lacked the industrial capacity to match it. The pressurized cabins that seemed impossible to duplicate in 1944 became routine in 1950s. But timing mattered decisively. American engineers solved these problems years earlier, giving American forces technological advantages that proved war-winning. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.